So if you watched the 2 previous videos, you learned how to code, and then we made a game. But now let's get ambitious. We're going to try and make a 3D wireframe engine. Maybe not exactly the wisest thing to do if this is your first day coding, but I don't care. If I knew how to do this 14 years ago, I would have been thrilled. So how are we going to go about doing this? Well, first we're going to start by taking the code from our other project and copying it. Oh wow, and look at that. Who would have thunk it? When you already have the code written out, doing 3D is easy. So the problem here now is that this is in the wrong language. So let's fix that. So clearly I'm the least prepared for this section because, it's not like I had this planned out. I was literally coding this for the first time in JavaScript right now. But the core of everything is happening in this draw 3D line function. Basically, this one statement right here, dividing trans x by trans z, which is the translated x and z values, is making things into 3D. Now hold on, I did not explain any of this yet, but let's just comment these lines out. So the first way that you probably want to construct a 3D engine is that you handle it from a top-down view to make sure that you got the math right. And so you saw before we were moving through those pillars, and here's what it might look like from the top down. So John Blow has a video on YouTube called How 3D Engines Work, and he probably explains this much better than I will right now. But imagine that this right here is our player, and this right here, in case you can't tell, is a building with a person standing on top of it. This right here, this is our screen. And in essence, we're projecting each point onto the screen. Problem, that doesn't actually help you understand what's going on here. And these for loops help make everything look more elegant, but it certainly doesn't make it easier to understand. So I'm going to unroll them. Okay, so I unrolled the code, and this is the view from above. It works the same as before. So draw 3D line takes in 6 parameters because a line is defined by 2 points, and in 3 dimensions a point is defined by 3 values. Our player also has an x, y, and z value, and we're getting the difference between each of the coordinates and the player's position. Hold on, let me just make this slightly easier to read maybe. So then this formula right here is called rotation around an axis. Now I didn't have this formula memorized. I just went to Google. Okay, I found it. This is the rotation page. And Wikipedia goes and it defines it for us here. X cosine theta minus y sine theta is equal to our new x value, and same with the y. So I just copy that formula, and that does a rotation. If you hate trig, that's fine. You could probably use linear algebra and avoid cosines and sines altogether, and that's probably faster. You probably should be using quaternions. But those are all concepts that I didn't feel like understanding. The point is that this is all sort of duplicated code, and in fact I don't even think we're using the y values here, so that's kind of like extraneous. But while this kind of looks like a lot of math, I mean these 3 lines are essentially all that we're doing, right? We're just doing it for all of the points. Okay, wait, no, hold on, we need z1 diff. We do need z1 diff. So yeah, this is the simplest representation of what our 2D engine is doing. Fpang here, that stands for first person angle, and this represents which way our player is looking. So if I go down to control logic, you'll see that when we turn right, we turn to the right, we increase the angle, and when we turn left, we decrease the angle, which looks like this. Right, so I turn to the right, walk forward, turn to the left, walk forward. And then when you press up, math.sine of the angle is just getting the x component, and math.cosine of the angle is just getting the z component. And then we're just adding that to the player's value. But that's it. That's all the cosine and sine that we have to deal with here. And to sort of explain what's happening with why we're finding the difference, and then why are we multiplying the difference by these angles here, it's because when we subtract off the player value, it's going to now treat player's value as sort of an origin point. And so that way, if we're going to do a rotation around a plane, which is what we're doing if we're moving a point like this, right, around in a circle, So we might stop here, and then that's a 90-degree rotation. The question is, how much are we rotating it? Well, we're rotating it by the player's angle, and it's negative, so that way left turns left and right turns right, because otherwise it would be reversed. And really that's all. So again, pretending that our coordinate's at 0, running the rotation formula that we stole from Wikipedia, given our player's angle. And then lastly, we need to add the center of screen X. And since our screen is 800 by 600, that's half of that, so that's 400. And we do that because otherwise our points would be rotating around the top left corner of the screen. So now if I go and change the center of screen X and Y to 0, you'll see that happening. Right? It's no longer rotating around us, it's rotating around the top left corner. But now you might be kind of wondering, like, well, okay, where did these squares come from? Well, so drawing a prism, and obviously we're drawing a square, so you don't have to do this. But you'll see I have this function that's drawing 2 pillars on either side 8 times. And what does draw pillar do? Well, it just draws 3 prisms, one on top of the other. And how does draw prism work? Well, it does it by drawing 12 lines. You might know that a prism has 6 faces, 8 corners, and 12 edges. And those edges are the lines that we're drawing here. And this is just pretty rote given your x, y, and z value and your width, height, and length of that prism. You could go and put your own shapes in the paint screen function. It just helps to have actual structure because otherwise you'd just be seeing abstract 3D lines in space. So I don't know if I showed it earlier, but here's the draw line function. So you could go and draw your own 3D line like I'm doing here. And you'll see, oh, we drew a 3D line. So now if you can get this top-down 2D rotation working like this, then it's really not that much more to go from this to a 3D engine. So, I mean, actually, all we're going to do here is we're going to define a new variable called screen distance, which represents the distance between the player's eyeball and the screen. Then we just divide our translated x value by our translated z value, and then multiply it by the screen distance. And we do the same thing for the z value, but we're dividing by y in this case, the translated y. Wait, that doesn't exist. Y1 diff, because we don't have to translate y. We would have to translate y if we were looking up and down, but we're not really caring about that right now. And then just repeat that. Okay, and that's it. Let's go see if it works. And yeah, let's get rid of our point from the center of the screen. And yeah, there we go. We did it. Wait, hold on. What's happening? What's happening? Oh God, what's happening? Oh no. So you might notice that everything works fine as long as everything is in the shot all at once. But as soon as you turn around, it's kind of like you got eyes on the back of your head, because that's actually what's happening. Right? So if you look at this from the lens of we're seeing both forward and backwards at the same time, that's what's happening. So we need to go and add one additional thing to stop that. So the translated z value represents how forward or back the point is that we're looking at compared to the player. So if it's greater than 0, it's in front of us. And if it's less than 0, it's behind us. If we just say, oh, if translated z1 is less than 0, or translated z2 less than 0, return, just stop the function. And now we don't have eyes on the back of our head. When I was coding this in C++, I was having problems with actually doing this. And I'm just kind of surprised actually that this is working properly. I had to set that number to 40 in C++ because otherwise it was just glitching out at the middle of the screen, probably due to like floating points, but you'd think that JavaScript would have more problems. But look, we can just get like right up close to this. That's incredible. I can't believe that this is working better than my C++ version. And it's like not even having any slowdown either. I guess that's it. I guess that's a 3D engine with wireframes. So why does this work, right? Why does dividing the translated x value by the translated z value
and then multiplying it by the screen distance. Why does this translate into 3D? Well, the reason is because of like trigonometry or something. Well, okay, so it's a similar triangles thing, actually, to be fair. So remember that diagram from before? And you can imagine that if we're going to draw a line straight to this dude, well, if we drew a line perpendicular to ourselves, we'd be drawing a similar triangle, like that. This right here should be proportional to this line right here. We know the distance right here because we set it to be 400. So if we know our z distance, which is this is our z distance, and this line right here, this is our y distance, and we know that because we know the real coordinates of this thing, because this would be our start point and end point of our lines. And we also know the y distance because this is just another real coordinate. So then it's just actually just a similar triangle proportion thing. You just say 400 over z is equal to, right, what we want to know, our question mark, over y. So then all you've got to do to get the question mark by itself is just multiply both sides by y, and you'll see that 400y divided by z is equal to our mystery value here. That's why there's no cosine or sine here, because it's just similar triangles. One interesting thing about this screen distance is that this is actually our field of view. So if we increase this value to say 100, it's going to start looking like that Quake cam, right? Where it's like everything like looks weird and things distort at certain angles, but it's because our eye is closer to the screen, and so it's like more wrapped around us, and oh god, everything is so weird. But this is because we've got a very large field of view. And similarly, if you pull that screen distance away, you're going to have a much closer field of view. So it's kind of like you zoomed in on something. 400 is a 90-degree field of view, which is pretty standard for 4x3 at least. But you know, I kind of want to go further. I want to go into uncharted territory, something that I haven't done. Let's try and solve the hidden objects problem. So what is the hidden objects problem? Well, so these are wireframes. And if you could imagine that we were drawing, say, some polygons between where the wireframes were, they should block out the pillar behind them. But that'll only work if you draw these things in the right order. And figuring out the right order to draw these in is actually kind of a difficult problem. So let's see if I can solve it. But first we have to change from drawing lines to polygons. We're going to make a new function now, and we're going to call it draw quad, because we're drawing a quadrilateral. Okay, yeah, I guess we gotta have an x3, y3, and a x4, y4. So we start at x1, y1, go to x2, y2, finally x4, y4. And so because we switched from drawing edges to drawing faces, drawing a prism is slightly different. So I guess I'll make a fill prism function. Draw 3D quad. And it's going to be pretty similar to the other one, but just like more stuff to do. I think you could just imagine it being like draw 3D line. Just instead of 2 points, we now have 4. And so, yeah, this is where you'd probably want to use a for loop to make this look more elegant. I'll keep it unrolled for the sake of easier readability. But I did mention earlier that copy and pasting things is kind of bad. Oh, this is tedious. But luckily, like once I write this once, it just becomes a lot easier. So what is that, like the top face? Because that's where X and Z change. Okay, it really helps knowing that you only have to worry about 2 corners because they're connected to 3 of the faces. God, I hate thinking about prisms abstractly by their faces and corners. What's prism? Harpy. No, harpy. No, it's not it. Apron? Oh, nice, a birdie. Hopefully that works. I think we could just copy the draw prism here and just say fill prism. X1, Y1, Z1, X2, Y2, Z2, X3, Y3, Z3, okay. And oh, all right. Okay, whoa, whoa, there's some weirdness going on. What? Okay, I think I broke something. I probably did did something wrong. It's like twisting the wrong way or something. Like that's what it looks like, doesn't it? How would it twist the wrong way? So yeah, let's just swap the 3s for 4s here. And oh god, no, I broke it further. This again. What in the world? Like again, this looks kind of cooler. Okay, so I think I did that wrong. Oh, wait a minute. I forgot. Okay, x1 zif, z1, x2, x3. Okay, yeah. I forgot here. This is my problem. I forgot. Okay, yep, it's working fine and boring now. Actually, to better demonstrate the hidden objects problem, let's make all the pillars different colors. Okay, I think we might be able to say RGB. Let's try that first just to see if it functions. Okay, yeah, whoa, look at these gray pillars now. Hold on, if I fill it first, it'll like draw the lines over it, and it'll probably look kind of weird, actually. Yeah, okay. Wait, whoa, what in the world? It's already blocking it. Does that happen from this side? So you'll see, okay, so if I go like this, you'll see from this side, these objects, like you can see right through them. And I guess I'll try and replace 127 here with what is it, math.random times 255. Okay, and that should just give us, wait, this is gonna this is gonna flash. All right, fine. I'll move this out of here. What's 255 divided by 8? 31. So let's just do 8 times 31. Again, I could just do 32 here, but whatever. Why'd I say 8? This needs to be I, you fool. Also, we don't need to parse int it because it's already an int. Wait, this is just going to make them all different shades of gray. We can modulate it. Yeah, modulo. Okay, so if we do plus 2 and then mod 8. That way it doesn't go over 255. And then we can copy this. And then we could say plus 5 mod 8. And there! Look at that. They're all different colors now. And see, look at them being weird and drawing over each other. That's not good. We don't want that. Right, it works the other way though. Right, so actually what we're going to want to do is that instead of drawing the quad, we're just going to save it to an array, because we're going to sort all the quads in order of how far away they are from us. This may have problems, but it might be a good enough solution for now. So let's change CTX draw quad here. Let's make this from a function into an array like that. And we can say quads to draw is dot push. We're going to push that array onto it. When we start our paint screen, we're going to want to make sure that quads to draw is empty. Okay, great. So it should draw nothing now. Yeah, good. So, I mean, really that shouldn't be called draw pillar. It should be like push it to the array, but I don't care. And then let's just do render quads or something like that as a function. Oh, and you know what we can do? We could have passed a color as a parameter here, but what we can also do is we could just have that be the last argument. So we could just say ctx.fillStyle is the last thing on here. So we just say for var I equals 0, while I is less than quads to draw dot length I plus plus. Wait, we need more. Yeah, we need our translated z values. All right, so add these all together and divide them by 4 to get their average. So our average trans z, which will drop here. Okay, great. So now we have our average tz. I wonder if JavaScript just has like a nice sort array function or something. You can give sort a function that you can define, and whatever you put in there will be how it decides to sort it. We can say quads to draw dot sort, and let me just paste it. So get rid of points, change this to quads to draw. So A and B are just the two things that it is trying to compare to each other, but since these are both arrays, our average trans z is element x, so we're just gonna say, yeah, 8 minus a, right? Does that sort it in descending order, or we want to draw the farthest ones first? So we might want to flip this around. Right, so now that it's sorted, we can just do ctx draw quad. There's gotta be a better way to define all these than typing this all out. Okay, whatever, not that bad, right? And then lastly, we just have to make sure, or we have to define ctx.fillStyle, so that way we get the right color drawn. Replace that last. Okay, will this work? My money's on no. I'm right, it didn't work. Wow. Wow. So we gotta do our debugging, right? If we go to the end, right, it's a big number. So it looks like it's working. Although, wait a minute. It's sorted in the wrong order. Not that that is gonna fix the problem, but oh, right. These need to be I. I was giving it an array. Okay. Why are they all fricking pink? Okay, there. Let's see if it works. So yeah, look at that. Look at that. We go through it and it's blocking it. Right? Look at that. Look at that. We have some yeah, look at that. Wow. So like theoretically, if we also wanted to, we could probably drop the lines if we wanted to do outlines or something like that, so you could see these better. But we could just color the top and the bottom differently. Let's go and do that. Okay, so if we do, we could set the fill style to, I'm trying to figure out like which prism is which here. And I just want to we'll make the top and the bottom darker. So we'll just say ctx.fillStyle equals, and this is where it's kind of annoying. Is there a way like JavaScript turn hex color into RGB? Okay, cool. So let's just copy this function from Stack Overflow. Let's just drop it here. So yeah, I don't really know how this function works. I don't really care. I just know how to use it. Yeah, so let me copy this ugly thing again. Hex to RGB. And then we're just going to change it. I think I'm going to have the values, which will make the whole thing darker. So get rid of this, change this to call.r divided by 2. You probably want to parse int it as well. That's probably a good idea. It could be like 0.5, and then it would not know how to interpret that. Right, so yeah, parse int call dot, what was it, g divided by 2, divided by 2, and we're parsinting that. So that should make the top and the bottom look different from each other. Oh, ooh, okay. We could see some problems with our engine here. Looks like PlayStation graphics. I mean, specifically with it like being able to see like unaliased edges and with it like glitching out when you're moving.
Like it's not that bad, but like obviously, you know, like you get stuff like that, and then it's, you know, it's clearly not functional. And like lit, I don't even know how you might go about fixing that. Okay, so like here. Okay, so you know what the problem is now that I realized it? The problem is that we're only taking the z values into account, and so like it thinks those two things are right at the same spot because they are. But we'd also have to consider the y value here, so we'd have to factor that into the equation because that matters too. So we'd have to do like more math. I don't feel like doing that. I think this kind of shows you like the basis of how you would start going about programming a 3D engine. I think like this is like the bulk of the tricky amount of work. And from here, you'd probably be able to figure out how to stretch textures to fix them across things and how to do collision. You know, it's just, I think the initial math and just getting anything at all is just like, you know, pretty difficult. And it took me a long time. But you could see that, you know, we have a mostly functional 3D engine. And I hope that if you were following along with this whole thing that you learned something. So I guess the thing that wouldn't be obvious is how you would start doing lighting. And like legit, I don't even know how you'd start doing lighting. I guess yeah, you'd start by maybe creating a light source that had its own position. And how does light work anyway? Like it just like fades out over time, right? So I guess you'd want the, depending on how far away from the light source you are, it would get darker. You'd also have to figure out how to get the light to, you know, how to do shadows and how to get the light to reflect off the wall or whatever. Maybe what might be important is how do you get mouse input to work? Because right now I have this controlling with the arrow keys, but I think, I mean, that's not too bad. You just, you have to add a mouse listener in the same way you add a key listener, so you could just Google that, and then you just like, I think constantly would put mouse at the center of the screen, and then you would, whenever the mouse moves, you just check how far away it is from the center, and that's how far you move the camera. Now, up and down might be a little bit more complicated, but you could probably do it by just sort of applying the formulas in a similar way. So I'm going to go and put all the code for this within the description, linking it to my website, as well as that link to the Jonathan Blow talk, how to create 3D engines, if you want to get a better understanding of how these things work. Anyway, so I want to plug my game again, Collapse Relapse on Steam. I'll put a link in the description, but it's a Metroidvania time loop game where you collect items to get more items to progress. And you only have 1 minute to escape, but you keep your knowledge of the map over time, as well as if you're playing in the default mode, only one, you get to keep one item. But past even completing the game, there's a lot of secrets. This 3D engine stuff may be relevant to it. And if I scheduled YouTube right and actually managed to edit my 8 hours of content down properly, it should be out now. And for the first week of the release, it'll be $2.99. And one of my core inspirations was not Minute, as you might expect, which kind of has like the same concept, but a game called Broken Cave Robot. In Broken Cave Robot, you've got 5 minutes to escape. But the problem with the game was that you had to make your own map. So I never actually managed to complete it, and I didn't even play it for that long. I kind of just wanted to make a version of this game that I liked more, essentially. And the graphics are heavily inspired by The Neverhood. Honestly, this is one of the best adventure games ever made. This game is fantastic. It mixes humor and atmosphere so well. And I mean, and it's also just like one of the coolest looking games. One of these days, I really hope EA will get around to actually putting this on GOG. This game is fantastic, highly recommended.